Hey guys, welcome back to Chilifili, and in this video I'm going to show you what is exponential regression and how we can implement it using Python in three different ways. So first of all, we need to know what is exponential function. Okay, let's take an example here. Let's say 2 raised to 1 equals to 2, 2 square equals to 4, and 2 cube equals to 8, and 2 raised to 10 equals to 1024. We all know that. Okay, so I have taken an exponential function here, that is f of x equals to 2 raised to x. So whenever I increase the value of x, the value of f of x is going to increase. But here you can see that we just increase our value of x by 1, but in our f of x value or our output value is increasing exponentially, or it is following an exponential pattern. Okay, so here this function is called an exponential function. Okay, so there are some real life examples in which you can note exponential growth, that are microorganisms in culture, spoilage of food, human population, compound interest, and more importantly, the current ongoing pandemic COVID-19, then Ebola epidemic, invasive species, fire, cancer cells, and smartphone uptake and cells. Okay, so you can notice exponential pattern in these examples, and there are many more in real world, but I have just listed a few here. Okay, so first of all, we need to know how exponential function is defined. Okay, so exponential function is defined as f of x equals to a plus b into c raised to x, where a is the shift value, b is the y-intercept or multiplication factor, c is the base of our exponent, and x is the input feature, and f of x is our output. And we are going to take each of this parameter and we are going to plot it with Python, and I will show you guys different kind of graph that we can plot by modification of these parameters. Okay, so initially we are going to ignore the value of a here, but don't worry, I will get back to the value of a in later this video. Okay, so consider our main value or our main function f of x equals to just b into c raised to x, and I've ignored the value of a here. Okay, so I'm going to show you some features of exponential function by taking examples. So the first point is that you can see here that whenever I put x equals to 0, then this function will be a constant function that gives us the y-intercept b. So we all know that what is the value of y-intercept? Y-intercept is the value when our x equals to 0. Okay, so when x equals to 0, it gives us the y-intercept that equals to b. Okay, the second point is when b equals to 0, the function simplifies to f of x equals to 0. Let's say f of x equals to b into c raised to x, so you put 0 here, then all of our function becomes 0, or it is going to be a constant function. So its output is going to be 0 for each and every input. Okay, so I have implemented it here using Python, and I've taken x as an array of that goes from 5 to 10 with an interval of 0.1, and the value of b is 0. As you can see, the graph is a constant value for every input of x. Okay, so the next point is when we take c equals to 0, the graph will also give the output of 0 for each and every input. Okay, so here our function was b into c raised to x. So if you take c equals to 0, then 0 raised to anything or 0 powered anything will be equals to 0. So our output will always be equals to 0. And I've also implemented it using Python here. You can see here that I've taken the value of c equals to 0. So our graph will be a straight line that has an y-intercept of 0. Okay. So the next point is when we take b equals to c equals to 0, then it's going to be the same. The output is going to be 0 for any input. Okay, now when c equals to 1, we can see that f of x equals to b. Here I have taken c equals to 1. Our main function is here b into c raised to x. So if we take b into 1 raised to x, then it will be equals to 1. So it will leave us only b. So as you already know, the value of b is the y-intercept. Okay, So whenever c equals to 0, our graph will always give us the constant value that is equals to the value of b. Okay, you can see here I have taken the value of b equals to 5, so the output will always be equals to 5. Okay, so many of you wondered that what if we take negative base into account. So here we are going to ignore, or we are not going to take negative base into account, because for many powers, mm, negative base gives us imaginary values, like that includes I and j. So we are just going to take only positive or zero values here as a base value. Okay, as you can see here that square root of -1 is equals to I, so that's an imaginary number, so we are going to ignore it. Okay, so here our actual function is b into c raised to x. So because we are only working with positive bases, c raised to x is always going to be positive, it is never going to be negative. Okay, so from that we can say that the value of y or f of x is either always positive or always negative depending on the value of b. If the value of b is positive, then the function or the output value is going to be positive. If the value of b is negative, then the f of x is going to be negative. So let's understand it by using an example. See, positive b value returns positive y value. Okay, see here I have taken b equals to positive 10 and the base c equals to 2. Okay, you can see that there is no negative value here. Okay, so negative b value returns negative y value. Okay, here I have taken b equals to -10, so and c equals to 2, so our function become -10 into 2 raised to x. So as you can see that it returns as a negative y value. It is here, this is negative y axis. Okay, so I think it is clear now that since we are only working with positive bases, our c raised to x function is always going to be positive, so our f of x is only dependent on the value of b. Okay, so moving forward, see, the base c determines the rate of growth or decay, and we are going to understand it by taking examples. See, first, if 0 is less than c is less than 1, it means that if our value of c is between 0 and 1, then the function decays as x increases. So smaller values of b leads to faster rate of decay. So let's understand what this means. So first of all, we are going to see how the function decays as x increases when our value of base is between 0 and 1. See, here I have taken 1/2, that is between 0 and 1, so it equals to 0.5 and 1 by 4 equals to 0.25. So you already know that 1 by 2 raised to 1 is greater than 1 by 2 square, that is going to be 1 by 4, so 0.5 is obviously greater than 0.25, and so on for all of this. So it is pretty obvious to know. Okay, after then we have defined the rate of change equals to new minus old divided by old into 100. I think I didn't write into 100. So if you write into 100, then it gives us the rate of change in percent. Okay, so let's see how this statement holds true. First of all, I have taken the example of 1/2, and then I'm going to take the example of 1 by 4. So 1/2 equals to 0.5, 1 by 2 square equals to 0.25. So the rate of change equals to the new value, that is 0.25, minus the old value, that is 0.5, divided by 0.5. And I'm going to take the mod of it, and it will return us 0.5. And I will let you know why we are taking mod here. First, let's look at the second example. So 1 by 4 equals to 0.25 and 1 by 4 square equals to 0.0625, and the rate of change we can calculate by the same formula, that is new minus old divided by old, so it will give us 0.75. So here why we are taking modes here, right, or why we are taking absolute value here. So we all know that the negative sign represents decay, and our exponential function has either decay or either growth. So the negative sign represents decay. To find the actual rate, we need to know the absolute value of it. So here you can see that the absolute value of the rate of change for 1 by 4 is 0.75, and the absolute value for rate of change of zero point 0.5 equals to 0.25. So here you can see that 0.75 is greater than 0.25. So in conclusion, we can say that the value of base c, sorry, the smaller the value of base c, the faster the rate of decay. So our rate of decay for 1 by 1 by 2 was 0.5, and our rate of decay for 1 by 4 was 0.75. So our value of c, that was 1 by 4 here, and that was 1 by 2 here. So as we decreases the value of c, our rate of decay increases. Okay, so that was our hypothesis here. When the function decays as x increases, sorry, that was clear from here, that as x increases, our function decays, or the value of our function decreases. So here I've taken x equals to 1, and here x equals to 2. So here you can see it is decreasing as x is increasing, and smaller values of b leads to the faster rate of decay. So here you can see that when the value of c equals to 1/2, then the rate of decay is 0.5, and the value of base c equals to 1 by 4 or 0.25, the rate of change is 0.75. So we can say that the smaller the value of base, the faster the rate of decay. Okay, so let's take an example to visualize it. So I've taken the first function as 0.10 to 25 raised to x. So you can see here the graph is here, and for 0.5 raised to x, we can see the graph is here. So here you can see that the graph here decays exponentially. The slope of this line is way greater than the slope of this line. Okay, so we can say that it decays fast or decays exponentially. Okay, so now moving to the second point, that if c is greater than 1, then the function grows as x increases. So it is pretty obvious from here. If we increases the value of x, then our value of our function is going to be increasing. Okay, so for that I'm going to find the rate of change as we did in our last part. So for 2 it is the rate of change equals to 1, and for 4 the rate of change equals to 4. So here we can see that the 4, which is the rate of change when c equals to 4, is greater than the rate of change when c equals to 2. So the rate of change here was 4, and the rate of change here is 1. So in conclusion, we can say that if c is greater than 1, then the greater the value of base, the faster the rate of growth. It is exact opposite of when value of c is between 0 and 1. Okay, so let's take some data and visualize it. Okay, as you can see here, the first function is 2 raised to x, so it is going exponentially here. And the second function is 4 raised to x. So here you can see that in this graph, it is going in a smooth fashion. Okay, but in this graph, it is almost straight till here, but after then it is going to be increasing exponentially. Okay, you can see here, but in this graph our function is let's say it is smoother than this function. Okay, the slope of this line is greater than the slope of this line. Okay, now we remembered we ignored the first parameter a from our function, so now it's time to get it back. And our main exponential function is f of x equals to a plus b into c raised to x. So here a is the shift value, which means that a positive a value will shift our graphs that much unit to positive axis, and negative a will shift our graphs that much unit in the negative axis. So let's take an example to visualize it. So first I'm going to take an example without the value of a, that is just the b into c raised to x. So it is here. Okay, and notice that the point here is 0. Okay, so now what if we take the value of a equals to plus 200? So you can notice that our graph shifts upwards, or our graph shifts from 0 to 200. Okay, so that is the function of the value of a. And if we take the value of a equals to negative 200, then our graph shifts in the negative y-axis. Okay, so here is the general exponential function that we generally see, that is e raised to x, where the value of e is 2.71828. Okay, and this is the graph of our exponential function here. Okay, so now we are going to study a little bit about natural log, because we are going to use some of these rules in our next derivation of exponential regression. Okay, so if you're taking a high school or college math class, then you will likely cover natural logs. But the question comes in our mind that what is natural log and what does the letter E means? The natural log, or ln, is the inverse of letter E. The letter E represents the mathematical constant also known as a natural exponent. Like pi, E is the mathematical constant that has a set value. The value of E is equals to approximately 2.7128. Okay. E appears in many instances in mathematics, including scenarios about compound interest, growth equation, and decay equation. Now, notice that ln x is the time needed to grow to x, while e raised to x is the amount of growth that has occurred after time x. Okay, so this is the point to be noted, that ln x is the time needed to grow to x, while e raised to x is the amount of growth that has occurred after time x. Okay, so now we are going to take a look at some of these basic rules of natural log. So first one is product rule. Then whenever we have product, then we have to add it. Okay, and this is some basic rules that you already have known in your high school or college classes. So we are just going to quickly go through it. Then the second rule is quotient rule. It is division. So whenever there is division, we do subtraction operation. Then the log of 1 equals to 0 and log of e equals to 1. And the reciprocal rule states that ln log of 1 upon x equals to negative log of x. Here ln means the log with the base of e. Okay, we have many bases in mathematics like 2, 10, and many more, but here ln means log with base of e. Okay, so log, sorry, we are just going to say it log here. So log of 1 by 8 equals to log of 1 minus log of 8, as you can see here in our quotient rule. So as we all know that the log of 1 equals to 0, so it leaves us with log of 8 with a negative sign. Then there is a power rule that log of x is to y equals to y into log of x. So the exponent comes forward with multiplication with log of its base. So log of 2 raised to 3 equals to 3 into log of 2. Okay, so before we move forward to the implementation of exponential equation, I hope you already read my previous article, or you have already watched my previous video on linear regression using normal function. Since we are going to use almost a similar method to implement it, and if you haven't already watched that video, then I'm going to put the link in the description. That is a very easy method, and we can perform our operations fast when we have low amount of data points. Okay, so I very much recommend you that you take a look at that video first. Okay, so now moving forward to the implementation of exponential function in Python. So as I said earlier, we are going to take a look at three different methods for implementation of exponential regression. The first method is without libraries or from scratch. I'm not going to use Python libraries such as SciPy to implement or find the optimal parameter values like A, B, and C. Okay, so first we are going to perform it without libraries, and after then we are going to use libraries. Okay, so our main function is y equals to b into c raised to x. Okay, here notice that c equals to e raised to c, but in general we write it as c. So in our derivation, the function we will be working with will be b into e raised to cx. Okay, so I think that is easy to understand. Okay, so now we are taking natural log both the sides, and this equals to ln y equals to ln b plus c into x. Now, why it is equals to c into x? Because we know that the power rule, that is ln x raised to y equals to, the first here is the value of y. Okay, so what is the value, what is y here in our case? Our case y equals to cx. So first we have cx into the log of x. Okay, the log of x. So the value of x here is e. So the log of e equals to 1. So we are just writing it as cx. Okay. So since we are going to use the normal equation, we need to represent our data in matrix form. So we want to find the parameters that are stored in this vector, y vector. So we are going to take, we are going to go according to our formula. So we are going to first take the natural log of y. So okay, and we have just x value here, and see, the value of d holds the coefficient of ln b, and the value of c is the coefficient of x0. So we don't need to do anything with the value of c, but we will perform some operations on the value of d once we find the optimal parameter, and we will get back here when we find or we perform some operations on value of d here. Okay, so normal equation is x transpose into x inverse into x transpose into y. So our theta holds the value of optimal parameters. Okay, so moving forward to the Python implementation. Okay, so I already have the Python notebook in Jupyter. Okay, so first of all, we are going to import some required libraries, that is NumPy, Matplotlib, and Math. So in just 5 to 7 minutes, we are going to need to implement, or we are going to need to find the value that requires us to import the library math. Okay, so I will let you know when we will use it. So I'm going to run it. Okay, it ran fine. Then okay, this is the basic data set that x has the value of it goes from 1 to 10 with an iteration of 1. So it goes from 1 2 3 4 5 6 7 8 9 10, and the y is the b into c raised to x. So I've taken b as 1 and c as 1, sorry, c as 2. So it becomes 1 into 2 raised to x. Okay, so now I'm adding some noise to calculate the error rate. Okay, if you don't add this noise, then it is fine, because here we are going to generate some, we don't have, we don't already have our data set like we have in our CSV file. So to make our data look more realistic, I'm going to add some noise to it. Okay, so I'm going to grab the np.random.rand function that has the length of so the length of y is the number of points that is going to be generated. Then I'm going to add to our y function, so our y value will be noisy. Okay, so I'm going to show you. Okay, it's going to take some time. Okay, here we go. So you can see here that if we hadn't plotted our, sorry, if we hadn't add the y noise, then it was probably not this messy, or it is not that messy, but you can see that the points here are not that synchronized. Okay, so okay, let me just quickly, let's say y, small y equals to 1 into numpy dot power and 2 raised to x. Okay, and I'm going to scatter it. are going to plot it in a scatter plot. Okay, so here you can see that if you don't add noise, then it is going to be just a simple function. It is almost the same, but if you look closely, then you might notice some difference here. Okay, and if I increase the value by 30, then you might probably notice some more difference. Okay, so here you can see that the second point is shifted upwards, and the fourth point is also shifted upwards. Okay, so I'm going to just keep it to 10. You don't have to worry while you are working with some real life data or any kind of data set that we have in CSV file. Okay, so moving forward, so this is our we are now going to form our matrix X. So for those of you who don't know why we are going to form the matrix X, then let me just quickly show you why do we need the matrix X. Okay, and here is my blog if you want to check it out. I post all my articles here. Okay, implementation of simple linear regression using normal equation. This is what we need now. Okay, this is our function, and okay, so now we want to find the value of theta, and what we need to know is the value of x and value of y. The value of y is the output feature and x is our input features. Okay, so here are our data points, and we are going to plot it, or we are going to represent it in our matrix formation or matrix representation. Okay, so here beta 1 is the coefficient value of x. Okay, so if you multiply this matrix, then it becomes 1 into beta 0 plus 1 into beta 1 equals to 1. Then 1 into beta 0 plus 2 into beta 1 equals to 3, and 1 into beta 0 plus 3 into beta 1 equals to 2. So as you can see that 1 is always going to be the coefficient of beta 0. Since we are going to form a matrix representation, the value of this column should not be left 0. So we are going to take the first column as 1 always. Okay, and the second column is the value of x. Okay, so moving forward, and if you have more than one elements here, then you can always add number of columns here. Okay, so get back to our main data. So this x bias is nothing but the column, or this first column here, so that is length of x. So I'm going to just show you guys the shape of x, that is 9 comma 1. Now the shape of x is 9. So we need to reshape our x matrix, sorry, the x vector, since we want to append our data with it. You can see here we have appended the x matrix, or sorry, the x, let's say x column or x data points with one vector. Okay, so you can see here we have appended it with the vector 1. Okay, so for that we need to reshape our data to 9 comma 1, or the length of our elements in x comma 1. So as you can see, okay, so now moving forward, so if you remember that we need to find the value that has log y. Okay, you can see our function has log in the y side, so we need to find the log of our output. Okay, here we go, and then we are going to perform this operation. We are going to append this. Okay, so appending it using numpy, then we are okay. So what we need to do now is find the transpose. See, we have performed this operation until now, transpose into x. So we need to multiply now. Okay, so first here we're going to need to find the, okay, there is some error here. All the inputs array must have same number of dimensions, but okay. Okay, let me just do, what is the error here? I'm going to run all of the data again and see if there is any problem here. No, it was just some glitch. Okay, so here I'm performed the append operation here, and then I'm going to find the transpose. So here is the transpose, and then we are going to multiply it with x. So here I'm going to perform the multiplication operation. So transpose dot x new. Okay, and the next operation is inverse. This is the linear algebra dot inverse. So it will give us this value. So now what we need to do is find the transpose value into y, then we are going to multiply it with each other. Okay, so notice that we have saved this or stored this variable, or sorry, stored this product into variable called temp1, and we are going to store this variable or value to variable called temp2, and then we are going to multiply it. Okay, so this is our temp1 and this is our temp2. Okay, so now what we have is our value of theta here. So theta equals to temp1 dot temp2. So these are our coefficients. So the first is our value of beta 0 and the second one is our value of beta 1. Okay, so now what we need to do is we need to plot a curve from our data. Okay, so for that we are going to import the math function because we need the value of e here, or you can just type the value of e here, 2.71, it was something like that, 2.7178. Okay, but I'm going to use the precise value here. Okay, so clearly you can see that the value of c equals to theta 1, so that is nothing different here, but the difference is in this value of b. Okay, so if you guys remember that I told you that we are going to get back here, so we are going to get back here. What was I talking about? Okay, here we go. So now what we have is the value of d here is stored in the value of theta 1. Okay, sorry, in the value of theta 0. So this value 0.91 is our value of d. Okay, so now what we have is in our formula is the value of b here, but what we got is the value of log b. So to convert the log b value to our original value or the value of b, we multiply it, sorry, take it we take the base as e and then take the power as our theta 0 value. Okay, so let me say that if we have, okay, ln of b and we want to find the value of b, then what we do is we take the power of e raised to b. Okay, so that way we can get the value of b. Okay, you might have already heard about in your high school or college lectures. Okay, so now what we have is we have our value of b here and value of c here. That's all we needed. So I'm just going to find the predicted value from our graph, that is the b dot math into e raised to c raised to x. So why am I doing this? Because that is our main function, e raised to cx. So here c into x, then I'm going to perform the exponent operation. Okay, so first of all I'm going to plot our main data, that was x comma y, and I'm going to plot our regression line or regression curve or the exponential curve using x comma y plot. Okay, so the y plot is the value we just found here. Okay, as you can see here, we have our model has done a pretty good work. The error, okay, so now what we need to find is the accuracy of our model. So that for that we are going to import our matrices and the R2 score from it. So the R2 score calculates the accuracy of our actual data points, that was y, and our predicted data points, that was y plot. Okay, so our accuracy of model is 0.95, so that's good. Okay, so now moving forward to the second method, or the second method was using it without libraries, or performing this exponential regression without libraries. Sorry, I'm sorry. The second method was implementation of exponential regression using SciPy library. In the first part, or in this part, we saw how we can perform it without SciPy library. So we had to find all this operation, or we had to perform all these operations to perform or to find the value of theta or the value of our optimal parameters. But using SciPy libraries, we just get our value of optimum parameters in just 2 to 3 lines. Okay, so now what is the disadvantage of a normal equation? So it is slow if we are working with larger data sets, normally 100K, okay, or 100,000. Okay, so now let's get back here. So it's just importing the libraries, and okay, I'm going to take a different data set here, that is day and weight. The day goes from 0 to 8, and here's the weight. Okay, and this is our exponential function here, that is x comma a comma b, and it returns a into b raised to x. Okay, so this is our definition of our main function or exponential function that returns as a into b raised to x. So our function is generally a into b raised to x. Okay, so in our previous section we had to find the value of our optimum parameters by all such calculations, but here you can see that we already found our value of our optimum parameters in just one line. Okay, here POPT, this value or this variable, stores the optimal value of our parameters, and PCOV is the estimated covariance of POPT. Okay, so the covariance is nothing but the interrelationship between the variables. So how do we find the value of our optimal parameters? So this is the function for that curve fit, and it takes 3 parameters or 3 minimum parameters. The first one is the function that we want to apply it on. So this is our exponential function, and the data it requires, that is the day and weight. Okay, so that was our data set here. Okay, so now what we are going to do is we are going to predict the value of our weight. Okay, that was our dependent variable. So we are going to predict the value of weight here using the expo function, and we already have a, and we already have found the value of a and b here. It is stored in the POPT variable. So the a value, sorry, the a value is stored in the 0th index, and the b value is stored at the first index. So we are going to write it like that. Okay, and you can see the POPT and PCOV value here. Okay, so now we are going to plot our data and the regression curve. So that is pretty easy to understand for you guys. Day and weight, and the red line, and then scattering the data, and these are just labels, nothing special here. Okay, so now I'm going to check the accuracy of the model, and it is same as how we did it here. Okay, so you can check it here, it is pretty good, 0.99. Okay, so here you can see that this method was very simple, but it is always good to know what we are working with and what is the logic of our exponential regression and how it actually works and how it actually calculates the value of its coefficient. But you can always use this Python library called SciPy to implement your exponential regression program. But I've already shown you this method if you want to perform it like that, and it's always good to have some knowledge on how the calculation actually work. Okay, so now getting back to here. Okay, so now what we are going to do is we are going to find our value or our value of parameters from scratch. Okay, So if you guys have watched my previous video or read my previous article, then I already wrote an article about how we can perform the simple linear regression from scratch. So we are going to use the same formula here that we used in our simple linear regression. So we are not going to waste our time by talking about the same thing here. Okay, and I will put the link in the description if you want to know how this the calculation actually work. Okay, so here our main function are the value of our coefficient a and b. So here what we are going to do is just replace our value of y with the log y. Okay, so let me get back here. So our main function is this, and we already talked about this. Okay, so now our function is ln y equals to ln b plus cx. So it is seems like y equals to a plus bx. That is the equation of line. Okay, so we are just going to replace this value by this values. Okay, so it will give us our optimal parameters. So here I have talked about all this stuff here that we have already talked in here. So I'm not going to waste your time by talking this again. Okay, so let me just quickly get to the point. Okay, so now we have our optimal parameter values here. So we are just going to replace these values by our actual values in this exponential regression. So replacing y with ln y and a with ln b and capital B with c, we get these values, and we can actually now implement our Python program from scratch. And I've already implemented it from scratch. If you want to have a look at it, then I will put the link in the description. Okay, so here you can see how we can calculate the value of our slope and intercept from scratch. Okay, so I've used this function only to find all the value of slope and intercept. Then we are just going to plot the data and check the accuracy. Okay, so I'm going to put the link in the description for the video and this article also. So if you want to have a look at this, and it will give us, or it will give you strong intuition how the actual calculation works. Okay, so that was the third method from which we can find the value of our optimal parameters. So that's it for this video, and I hope you guys enjoyed it and learned something new from it. And if you really enjoyed this video, then please hit the like button, that will encourage me to write such in-depth explanatory videos. And okay, so thank you very much for watching, and I will see you guys in the next video. Okay, and if you want to read my articles, then they are all available on my blog, and I'm also on Medium if you want to follow me there. Okay, so thank you so much for watching, and I will see you guys in the next video.